do is I'll have you collect them from either me or the TA. So after class, you have to tell us your name, and then we can hand them back to you. I just am seeing these now. I just glanced at the scores. It looked like the average score on the quiz was 85%, which is a bit closer to where I expect that the average is on most of the stuff. So to be for the semester than the homework. There may be some corrections coming on the homework as well. I've been notified a bunch of you got taken off, for instance, for not having code presented on the last question, question 4, but question 4 didn't actually ask for code. So we'll be, for those of you who had that, we'll be getting those back. So we're still doing these things. So if there are any other things you feel are unfair about it, you can so you can let me know about it. But those should be done like now. I won't accept those kind of concerns at the end of the semester. Should try and sort this out over the next week or so. Okay. So the quiz will be back after class. I think the class did, not everyone, but overall fairly good on the quiz. And if there are any specific questions about that, also you can maybe ask me after class or the TAs. That's a good thing to go and figure out if there's something you missed and you didn't understand. So then homework 2 will be posted by the end of the day. So I have homework 2 almost ready. I just haven't posted online yet. I found, or once someone in the class found a link to some answer key for some bonus questions from a previous year, which is great. Actually, so there are some extra questions on homework 2, which are worth 0 points. You don't have to do them, but there's an answer key which I can link to, so you'll get some extra questions and answers to look at. But the actual questions I'll ask you to do are going to be new. I'm not going to give you the answers for those. Yeah.
So are you giving the key out with those bonus questions, or do you have to say on the internet?
It's already out there. It's not hidden, like especially hidden if you know where to look for these things. So I think I'll just post it that way. You don't have to look at it, but I'd rather not be an unevenness between the people who already found it and those who didn't already find it. So I'll post the answers, which I think was written up by a TA in a previous a previous year. So I can post the link to those, and those of you who want to look at them while you're doing them can do that, or you can not look until they're afterwards, for those of you who like to read the whole book before the last chapter. So you can, maybe that's too much difficulty and you'd rather I not post them until for a while.
Go ahead and post them now.
Okay, good. I don't know how much the urge is to go and look at the answers, but sure. Okay, so I'll post those later tonight when I post the actual assignment. And again, my hope is that this one is more direct and there shouldn't be problems that are unintentionally as difficult as happened in the first one. But sometimes you don't know until you give them out to the class. So okay, and these assignment will be basically on the convergence section, which we finished last week, and then the linear algebra section, which we're doing the second of 3 lectures today. So you should be able to do most of the homework, almost all of it, starting today. There will be some stuff that you could have to wait one more lecture, or you may have, because it's a linear algebra review, you may have seen some of this stuff, hopefully already. All right, and so that will be due Yeah, so the homework 2 and quiz 2 will actually be, I think, fairly well aligned. The homework 2 will be due the Monday before fall break, and then the quiz 2 will be the Wednesday before fall break. So I kind of try to align those with fall break, so you won't have stuff to do over fall break. Hopefully that's a good thing. Yeah, all right. Fall is awesome in Utah, so hopefully you can take advantage of it. Great, so any other administrative questions? Cool, so, all right, so we're talking about, so linear algebra, and really this is I think of this as the language of high dimensional data, essentially. And so that's what we're using it for in this class. And so I set, but I think after registration opened, but I set Math 2270 as a prereq for this course. So if you haven't taken that, you hopefully can do okay. But so hopefully you've seen a lot of these things before. Hopefully I can give you a new or more useful and for this sort of material interpretation of this sort of stuff. Okay, and so we concluded the lecture on Monday before we took the quiz with the with the addition of like two vectors, and we wrote, say, two vectors x and y. These would be in RD. Okay, and so we would think of this as x. We're storing this as so this array x1 up to xd, or you can think of it as this ordered set. And so the ordered set is kind of the order comes from not that x1 comes before x2 so much, but that the x2 corresponds with x2 of y. So if I have y, I'm going to write y1, y2, and yd. And x2 and y2 kind of essentially have the same, they're representing the same thing. x1 and y1 are representing the same thing. So if I swapped the order of them in this ordered set, it doesn't change, and I change the meaning too, it's not really going to affect anything in this representation. So the fact that this one comes first doesn't matter, but the fact that it's aligned with y1 is what matters here. And so then remember, x1 plus, or x plus y is then going to be x1 plus y1, x2 plus y2, up to x2 plus xd plus yd. Okay, so it's important that when you add them, you're adding up the same element here. Okay, and so a different geometric way of seeing this is I can have the first and the second coordinate here. So if I have x here and I have y here, this is x1, x2. This is y1, and y2. And these give me the coordinate values. Right? So I think of this is x here. This one is y, and the y1 tells me the length along this axis, the x1, and y2, the length along this axis here. Right, so it gives me these two lengths here. Now the nice thing about adding these two together is that it's going to give a new point that's going to be up here. And so the way to think about this geometrically is that I'm just stacking these vectors together, and I can do this in either order, and I'm going to get the same answer. Okay, so I've taken the vector x, and I've added it to the end of y. I get x plus y. I can also take the vector y, and I can add this to the end of x, and I get the same answer. Okay, so and this works in higher dimensions as well. can't really draw in higher dimensions, but this is the way to think about adding, right? You're just kind of putting one vector after the other, and the result is the x plus y vector here, right? That's just a single vector up to here, or we can think of it as a pointer vector. Again, these are effectively equivalent representations. They're all just arrays. Okay. And then with addition, I can also add. Let me say I can add. Say I have two matrices. Remember, I wrote this as an n. These are n by d matrices. Then I can add them together as this large matrix, where this is A11 plus B11. Okay, that's this first entry up here, and each entry is just an entry-wise addition of these two objects. Okay, and it's not quite as nice to visualize in this way, but you can think of it as some extension of that as well. And again, what's important is that the space, the number of coordinates, the domain that they're in has to be the same, right? They both have to be d-dimensional vectors to add them for whatever d is. The matrices need to be n times d-dimensional matrices to do the addition. All right. Okay, so a multiplication. Okay, so multiplication is a little bit trickier. Let's talk about some matrices here, and we'll have the first matrix A be n times k, and B is going to be k times d. Okay, and they need to have, as we'll see, the number of columns of A will need to match the number of rows in B, right? So I can write A, B is going to be equal to C, where C is now going to be in n times D, and so, and then entry Cij, the ith j entry, the ith row, and the jth column is let me fix this notation so it aligns with the notes. Okay, so A will be n times D, B will be D times M, right? And then the D is what matching, and C will be n times M. Okay, so now we'll iterate over K1 through D of AI K times B K J. All right, so when you write multiplication of two matrices, then you just so you just put them next to each other. So it's like so like matrices are like rabbits. If you put them next to each other, they'll multiply. Okay. So it's usually there's not a dot written in there. The dot might implicitly imply some other sort of weird operation you can do with these matrices. So just write them next to each other implies multiplication. Okay, so we won't write a times or a dot or something else. There'll be certain special types of multiplications that will have symbols for, but for matrices, we just put them next to each other. Okay, and so to try and envision what's going on here, it's good to think of a matrix A that looks like this. And it's going to have n times n rows and d columns. Okay, and if we're going to multiply it by a matrix B, we're going to need the number of rows of B to be the same as the same as the number of columns of A, right? So the columns of A, the number of them is the same as the length of the number of rows of B. Okay? And so what's happened here is that the entry Cij, right? So I'm going to end up with a matrix that looks like this, right? This is N, this is M, and this is C. Okay, and so now Cij is this entry. It's the ith row and the jth column. Okay, what this is going to do is I'm going to fix row AI, right, which is the same row here. This is AI, the ith row of A. And I'm going to fix the jth column of B. I don't specify notation for the column so much, but this is the jth column of B here. And these need to be the same length, right? These are both, this is of length D, this is of length height D here. And I'm summing over the entries and I'm multiplying these together. That's filling in this entry here. Right, so if I shift I here, I change the row that I'm computing. I still have the same column in B, but I'm shifting this to a different row here. And if I change the column, I'm keeping this row entry, but I'm shifting what the column is here, and I'm getting the outputs. Right, so that's why I'm getting an N by M matrix here, because for every row of A and every column of B, this is going to give me a single cell here. Okay? And that's why these, under this definition, that's why the number of columns of A and the number of rows of B have to align, because I have to take this sum and kind of pair up each of these entries. Right? This is K equals 1, K equals 1 is in here. I take these and multiply them, and then I keep shifting this down here and kind of multiply these together, and the sum ends up in here. Okay, so this is the general definition of matrix multiplication here. And there are several special cases which I'll go through, which are maybe more important. But they're actually special cases because we'll consider when one or both of these are actually vectors. And if A is, say, if A is a row vector, then that means I just set n to be 1. And the same definition just applies. It just happens that that it's just going to be one column here because there's only, one row here. There's only one row here. Okay, so let's step through some of these special cases. But any confusion about the specific definition first, and we'll hopefully gain more intuition to go through the special cases.
It's kind of related to the concept, but so when you have very large amounts of data and you're using the programming techniques to solve matrix multiply, how do you worry about precision and making sure that it run? Do you worry about runtime speed?
So yes, this definitely becomes an issue with very large data sets. As I've alluded to, we'll have a large data set will represent as a big matrix. And if you can imagine with big data, you get millions and hundreds of millions or billions of rows of A, and the number of columns maybe hundreds of thousands, right? And when you'll need to do operations with matrix multiply will come up, and we'll see several cases where we'll use this even in this class. And that can be very slow. Okay, so if you just analyze the runtime of this algorithm, it is n times m for each of the cells, and each cell costs O of d time. And that's just kind of assuming everything is in RAM. So n times d times m. If these are all roughly on the same order, it's n times n and n, then it's n cubed algorithm, right? And for n being billion, n cubed is too slow often. Okay, so there are these fast matrix multiply algorithms that can get this down to like n to the 2.3 roughly, and they're still kind of trimming what that constant is. It might be as small as n squared. Those are, at some level, those are kind of practical at some scales. What's more common is to say, you know, in data analysis, there's a lot of, because there's a lot of noise involved in the process, you can often lose a fair amount of precision. And what we'll do is we'll actually what's called sketch a matrix and compress it to a much smaller matrix that captures the same information. And that will kind of, and just by reducing the size of it, we'll be able to kind of speed up the computation. This is something we mentioned a little bit in the data mining class I teach in the spring, and it's covered some of it in the book. And at very large scales, this is what is commonly is used inside, say, Google or Amazon, where they have to do this sort of stuff all the time. So it's a great question. So, yeah.
What are the names of those techniques that you're kind of referring to?
So matrix sketching is what you want to look at. If you look at, I think it's the last chapter in the current version of the book, it talks about some of those techniques. Yeah.
So I always get the is the difference between the matrix multiplication and the dot product? The dot product is just one of those entries, is that right?
Yeah, okay, good. So let's talk about some specific versions of this, and we'll talk about the dot product, and then we'll see how this embodies kind of is doing the dot product internally. Actually, I want to mention a couple other points first before we get into those. So matrix multiplication is associative, and so this means that A, B, C with doing this first is equivalent to multiplying B times C first. Okay, so when I chain these together, basically think of this as N times D, D times M. So like the part next to each other has to align. Then C would have to be M times L or something like that. But when I multiply them, it compresses that middle term, so that's okay. I can switch the order of computation from A times B, then C, to also doing A times product of B and C. This is legal. Now, the amount of runtime difference in these two operations might be massive. So the result is the same, but one might be much faster. If I'm able to first compress a very large kind of coordinate, so let's say D is much bigger than N or M, and I multiply these together, then the result is a much smaller matrix that would be fast multiplied by C, as opposed to the other way around. So the order can affect runtime, but not kind of what the answer is. Okay. So it's also distributive, which means that so I can add B and C together, then multiply by A, or I can do A, B plus A times C. Okay, so I can add first, or I can add afterwards. This is fine. Okay, but it's not commutative. Okay, so this means that A, B is not equals to B times A. Okay, so I can't switch the order of multiplication. Sometimes A times B is legal, but B times A would not be legal. The dimensions are not going to line up. Okay, so it's good to keep these in mind. Okay. Okay. What's the next simplest? So matrix scalar product. Okay. So I have a scalar alpha in R, and a matrix X in R n times D. Okay, then alpha X, again, I just put them next to each other, is going to be in n times D, and each entry of this is just going to be alpha times the entry of xi, right? So I multiply the scalar by every term, okay? So this is also true of vectors. Vectors inherit this because either n or d is equal to 1, okay? Okay. So now so what is, I think, most interesting, and I think will be the most kind of important operation, is a vector-vector product. And there are actually two forms of a vector-vector product. The most common one is called the called the dot product, or so sometimes the inner product. Okay, and so this will take two vectors, let's say P and Q, which are both in RD. They both need to be in RD. Okay, and so this is, and let's say this is typically written as, these are actually column vectors. And that is important if I write it as P transpose Q. So this is the common, if they're column vectors, I think of transposing P, and this is important. So then that means P started out as a D by 1 vector, and I transpose it so it's 1 by D. And then so that means P transpose is now going to be in 1 times D, and Q is in D times 1. Okay, so now the D's align with each other. Okay, another notation that I like better is to write them in these angled brackets. I think this has less confusion. I don't need to worry about whether they're column or row vectors in this case. Another one is common as P dot Q. And this is a dot in the center. It's not like a period. It's lifted up a little bit. In LaTeX, this would be C dot, for instance. And that's where the term dot product comes from, because they label it with this dot multiplication. But these are typically equivalent notations. And what this means is going to be a sum over all the entries of Pi, Qi. Okay, so I take the two vectors, right? So I take P, P1, P2 up to PD, and Q, Q1, Q2 up to QD. Okay, and I take the product of the first two terms, which are aligned, right? And then I do that with the second two terms and so forth, and I add all these together. Okay, so all of these are equivalent to each other, these notation. But we'll typically stick with this one in the class. Okay, so this is the dot product. Yeah, so and so the dot product is let me add one more thing. So this is a so it's what's often called a linear operator, so that if I have a scalar alpha, right? And I have x, y, and z in RD. Then I can do things like alpha times x plus y plus z, right? So this is, I can factor the alpha out. I can say this is equal to alpha times the dot product of x of y plus z. And this is also equal to alpha, the dot product of x and y, plus the dot product of x and z. Okay, so I can kind of factor out similar to, I mean, with follows from matrix multiplication, the properties of matrix multiplication as well. But these sort of operations are very useful in order to do. And in particular, the dot product has this really beautiful geometric interpretation of what's going on. And this will be useful when essentially I want to factor out the length. I want to have one of these vectors have a length of 1, and we'll define what this means kind of. So like in the next kind of part of this lecture. Well, but let's so assume that the length of x, which is in RD, is 1, and that will mean, just to skip ahead, that means the norm of x is going to be 1. Okay. So then then I want to look what happens at the dot product of x and y. Okay, so I'm going to assume that x, this is x and its length is 1 here. Okay, so I want to think of extending the line through this vector. There's some point here which is x. Okay, but its length is 1. There's a line through here, and then y can be any sort of length. So y is equal to 2, 1. So its length can be larger. Okay, y is this vector here. Okay, so what is this dot product doing? Well, I can think of this as representing a point here. Let's say this is a little bit more clear. I can think of this point here as a projection onto x of y. Is this point where what's happening is I'm taking this point y and I'm finding the closest point on the line that goes through x. Okay? And this is again a vector. These are all vectors in RD. In this case, it's R2. And then the dot product, x, y is equivalent to the length of the projection of x of y onto x, which is, as well, jumping ahead here, the norm. So the length of here from origin, the length of this vector up to here. Okay, so when one of the vectors has a length 1, okay, then I can think of the dot product as measuring the length of the other vector projected onto this subspace. Okay, so this is a really important intuition to have for stuff we'll do later on this semester. Okay, and so I want the length of this to be 1, and so I can kind of always take care of that, but I can, by setting x is equal to, say, x prime divided by the length of x prime, right? So let's say I wanted to do this with x prime, and I wanted to, I have this factor of the length. So what I can do is I can say that x prime y is equal to so I can of 1 over the length of x prime times x, the dot product of x and y. This ensures that the length of x is equal to 1. Okay, if I divide through by its length, all its coordinates, and that is a scalar multiplication. Division is a multiplication by 1 over that quantity, right? So I'm just scaling each coordinate by this amount, right? So I can factor this out of here, and now this dot product is 1 over the length x prime times the norm of. All right, so I can get, even if I don't have the length of x fixed, I can kind of get this and just factor this term out and still get this interpretation. But there'll be a lot of times where we will know that the length of a vector is exactly 1. Okay, so we'll do something to pre-process it in this way so its length will be 1, and this intuition will be very useful.
So if you were to move like x's length was longer than that, what would happen to that projected value? Would that just keep growing further up geometrically?
Yeah, right. So then basically I can do this projection, and then I multiply the result by 1 over the length, and that will scale it up here. But the dot product is not returning this value, it's only returning this length. So it's just a scalar. It'll actually be useful when I can actually recover this point by actually saying that this is equal to x, which is what's called a unit vector length 1, and then I can scale this by let's say here just the norm, which was the right. So I can recover this actual point here again by taking x, this vector, which tells me the right direction to go, and then multiplying by this, which is a scalar, which is scaling it up to here. So I can recover that point, and this will be useful.
Are you sure it's not supposed to be multiplied by the length of x prime?
Yeah, okay, good. So thank you. Yeah, right. So this was implicitly having a division inside of it, right? Okay, good. Well, thank you. Yeah.
So since we can only do that, like this is only the case when the length of x is 1, could we like factor out something from the x vector so it equals 1, and then do the. Oh, that's okay. That's
yeah. So I was trying to explain that you can basically always do that.
Okay.
You can always factor that out. This term is still lying around, right? So once I get the result, I have to kind of keep this term around if I factored it out. But often in data analysis, we'll start by saying, okay, we're going to have these vectors, these unit vectors, which will be these basis vectors, which will all have length 1. And then I can assume that the vector is length 1, and that's usually the situation. And that's when this is most helpful. Yep.
2 questions. So I'm just kind of confused. Why do we want that to be 1? Like, why is that a good interpretation? Or why are we trying to get it to have 1?
You know, we'll see much more later in the semester, but basically a vector is defining a one-dimensional subspace here. We'll define higher dimensional subspaces later on. I don't want to get too far ahead of myself. Actually, hopefully this lecture even. And then we want to find the closest point of y onto that subspace. And this will help us define it. Or just define the distance here, or the length of that point in here. And these will all be useful things to do to think about modeling a lower dimensional part of a high dimensional space. And this is kind of the key component that's embedded within the definition of the dot product.
And then second thing, would a dot product can be negative? Does that mean that the arrow is like pointing in different directions, or what exactly does that mean?
Yeah, so the dot product can be negative, and that would be that, well, the vector x is pointing in this direction. I could be that if y, let's say I've got another point here that z, its projection is down here. It's on the other side of the origin, and this is the length from the origin, and it turns out it's opposite of the direction of the original vector x. And that's what that's saying. It's giving a negative, kind of like a negative coordinate works. And we'll see much more about this. I just kind of want to see these thoughts for now, and we'll see them several times throughout this semester.
When we're talking about projections, our intuition would be to think about that point as like a particular representation of the actual vector y. If there's some information about y that we can ascertain having that point.
Yeah, right. This is a good way to start thinking about it. Well, good. Let's see these thoughts now. There's stuff you may not fully grasp yet, but hopefully we'll kind of come back to these things, and this will make more sense as this gets more useful. Yeah.
Sorry, I'm asking a lot of questions, but is like for some reason it's just like a little unclear. Like in most which scenarios we don't actually want to find the length of this projection. It's just not really concrete, like an example of like a situation that you'd want to find that length.
Yeah, so let me, there are kind of plenty of things we'll see throughout the semester. Let me give you a mention of something that we don't, that we won't see in this class otherwise. So one way of describing the distance between 2 points that removes their scale is, or actually the similarity, you want a similar to be larger, the similar should be larger the closer they are, is actually just to take, normalize both vectors so that they have a norm of 1, and then take their dot product. This is called the cosine similarity between them. Okay, and this is used for when there are vector representations of, you basically create a large vector of a document by counting how many times each word occurs, and that becomes an entry in the vector. And then comparing 2 documents, you often use this cosine similarity. And this is a useful similarity that takes out the notion of scale of the documents. Okay, there's lots of other ways, but this is one concrete place it's used. We'll see when we're doing dimensionality reduction, we have a bunch of high dimensional data points. We want to find a low dimensional subspace. We want to find the subspace which essentially is minimizing these distances, and that turns out to be equivalent to maximizing these distances. So then we'll think in terms of these distances. Okay. We'll see. Hopefully you'll see that this is useful plenty of times later. But this dot product is probably my favorite mathematical operator. So don't tell this to my son Max, who's named after a different one. Okay, but I guess that would be a girl's name. That would have been cute. Okay. All right. I don't need any more kids right now, so it's not okay. Okay, there's one other interpretation of this, and that, grab a different color, and that's to use this angle. Okay, I can define an angle in between here. I'm going to call this angle theta. Okay, now let's come back to this angle in a second, but the dot product of x and y is equal to the length of x times the length of y times the cosine of this angle theta. Okay, so I can also, this doesn't need to assume the length of x is 1, but if it does, then this one just isn't there, right? But it's a length of x times length of y times cosine of this angle. Okay, so I can also interpret it this way, and that means that you can derive this from kind of the law of cosines, right? I have a right triangle here, and I can derive this length, right, is what the dot product is, and then it's the length, this length of y is the hypotenuse, and this is the cosine here. Okay, so you can derive it from that. And what's neat about this angle, which is also really cool, is that I can actually always define this angle even if I'm in high dimensions, right? In this picture, I'm in 2 dimensions, and that seems convenient, okay? When you learned about angles in your geometry class in high school or something like that, you probably always wrote down stuff in 2-dimensional lines and so forth, and you can write down what this angle was. But even high-dimensional vectors, there's always a 2-dimensional space that goes through them. We'll talk about this soon. So I can always define, this angle is always well-defined in terms of like the 2-dimensional notion of angle. So this is kind of a valid concept even in high dimensions. So another way to think about the dot product. Okay, so the dot product is cool. One place it shows up is here, right? So we mentioned that this is a dot product. So that means this object right here is a dot product. Right, so it's a dot product between this vector, this row vector of AI, and the column vector, the j column vector from B. Okay, so this is a dot product, and every entry here is the result of the dot product, of the appropriate rows and columns from these other matrices. Okay. So one way I like to think about this, you write this here before I do some, move on, I do some erasures, is a matrix, so a vector product. So I'm going to have a matrix A in R n times D, and I'm going to have a vector in RD, and then I want to write down A of X. Okay, so in here, this has to be should this be a column or a row vector?
Column.
It has to be a column vector, right? So this is actually R of D times 1. All right, so it's technically 1 times 2. Okay? Okay, and so this is going to be equal to y, and this is going to be in Rn, right? And so y I can think of as the first row of A, so A1, dot product with X. The second entry is A2, dot product with X, up to AN, dot product with X. Okay, so one way to think about this here is that I'm going to have some matrix A here. This is A. I'm going to have this vector X here. And this is going to be equal to this. Let me write it over here. This is y1, y2, up to yn. Okay, and the way to think about it is I've got each of these rows of AI, and I'm taking this vector x, and I'm dot product with A, and it kind of pops out. The result is the dot product. So I take this, turn it outside, and I dot product, and out pops these values. Okay, and so when I'm doing, then if I'm doing matrix multiplication, I'm doing that each time like this, and this is giving me the first column here. Then I take the second column here, and I do this again, and this shoots out the second column, and so forth. And then it fills these all in. Okay, so that's how I like to kind of keep that straight. I get confused all the time about whether these should be transposed or not, and what's going on. This is, but this is how I try and keep it straight in my head. Yeah. Okay, and then I want to say, okay, one more thing about matrix products. Okay, so the other version is called the outer product of vectors. So P in Rn and Q is in Rd. And then this would be P times Q transpose. And here I'm assuming that they're column vectors, right? So now this is, so these are times 1, right? So the output of this is going to be in N times D. Okay, in the outer product, so then I'm going to get this entry, and this cell here, this cell, the ith cell, is going to be equal to pi times qj. I'm not adding anything up, it's just every possible combination ends up in a cell here. So I'm inflating the dimension in this case. Okay, so just mentioned there are these outer products, and in some cases these are a little bit useful to think about, but they're not nearly as common as the inner product of that.
Are they called cross product too?
Cross product is different. Cross product, the output of that is a scalar. Cross products are mainly useful in 2- and 3-dimensional thinking. They don't really generalize that much to high dimensions. So they aren't as generally useful for this sort of stuff we'll be doing. They can tell you a little bit about some things like volume, but the cross product is like super useful in things like graphics and robotics, where you're dealing with 3-dimensional space, which is the space we live in all the time, and that becomes useful there. Okay. Okay, probably went a little slower than I wanted on multiplication, but that's okay. Okay, so the next topic is norms, and this is how we define the length of the vector. Okay? So think the length. Okay, so if I have a vector in Rd, this is equal to v1, v2, up to vd, then the norm of v is going to be equal to this is the sum of the squared entries, all with the square root, right? So this is equal to v1, v1, plus v2, v2, plus vd, vd, right? Which is equal to the dot product of v with itself, or the square root of this. Okay, this is the norm. This is what measured this length. This measures the straight line distance from the origin to the vector itself. Right, so that computes in the geometric Euclidean sense the distance from the origin to the point that represents this vector. Okay, and then if the norm is equal to 1, then we say that this is so normalized, and that v is a unit vector. Okay, so this is a notation that will be useful when you think about dot products. If X is a unit vector, then all those nice kind of geometric properties hold. Okay, so this is what I mean by length. This is the norm. Okay. There's actually a much more general definition called these LP norms, and this holds for P in 1 up to, I guess, inclusion 1 up to infinity, basically plus infinity. A little bit weird notation. Okay, so this is defined. If I put a subscript P here, so the norm, I put 2 bars around here to distinguish the norm. The Pth norm is going to have a similar form to this. Equals 1 up to D of the absolute value of Pi of Vi to the power P, all to the power 1 over P. Okay, so if P equals 2, so that means that, okay, so when I write the norm in generally with no subscript, that refers to the 2 norm, actually. Okay, so that's just the 2 norm. I didn't need the absolute value because anytime I square something, it becomes positive anyways. Okay, but in general, you need the absolute value. So this is well defined as a notion of distance that's different than the Euclidean distance for all values of P from 1 up to infinity. The 1 norm turns out to be mostly the other useful one, except for you can effectively define this for infinity as the limit of, as P goes to infinity, of which is equal to the max of I in D of actually just the absolute value here. Okay. So just the maximum coordinate is the L infinity norm, and this is actually the same as here because everything other than the smallest one will just kind of get, when I raise it to the almost infinity of power, then only the largest one will be left over. All of the ones will be much smaller. And then I do 1 over the almost infinity power to get back to the max.
So when you have like norms higher than 2, so what do you mean by like distance for like higher dimensional things? Like say you would take like the 3 or like the 10th norm.
Yeah.
Something like what would that mean in terms of like distance? Because like with the 2 norm, you can like understand that it like represents like distance.
Yeah.
But when you have like higher dimensional data,
So there's a whole chapter in the book, chapter 4, which we will not cover in this course, which is about this sort of stuff. I'll give you, can't help myself, I'll give you a 1-minute answer here, but let's just look at distance from the origin, okay? And so this is the origin. And I want to draw a circle with all points at distance 1 under the L2 norm. And it gives me a perfect circle, right? It makes sense that you typically think of a circle as all the points exactly some distance radius from the center point, in this case the origin. Okay, so this is for P equals 2. For P equals 1, it looks like this. It's the sum of the absolute value of the coordinates. This equals P equals 1. For P equals infinity, it's the max. So it looks like this. This is P equals infinity. P equals 3 or something in between is kind of a ball that kind of has a square with rounded corners or something like that that comes out through here. It sits in between these, right? This is everything down to P equals 1 up to P equals infinity kind of slides outward in some way like this. And they give different notion distances between a point and some other point. And this, if you wanted the distance to be 2 instead of 1, you scale all these by 2 and so forth. So those are all about distances less than 1. It becomes not convex anymore, some concept we'll talk about later, and it kind of, you can define a distance, but it's not a metric. All these are metrics, and we have lots of those properties. Okay. Gives you a short answer to that. But if you're interested in that, there's a lot of cool stuff in Chapter 4, or you can take my data mining class in the spring. Okay. Yeah.
Sorry, this notation is called the L, what, like you'd say L of P.
This is the LP norm.
Okay.
This object is called a norm, and it's applied on a vector. If you want a general distance, you just subtract 2 vectors, and you get a distance, an L2 distance. Right? This is the L2 between P and Q. Is I do vector subtraction. I take the 2 norm, or P was a bad choice here, but right, I can check in general the LP distance between X and Q by taking their difference, and then their difference that gives me another vector of subtraction, just like addition, right? And then I take the norm, the P norm, and that gives me a different distance.
Oh, okay, that makes sense.
Yeah. Good. Okay, great. So these are vector norms. They're also so matrix norms. Okay, and the most general, I think the most intuitive matrix norm has an F. This is called the Frobenius norm. And this is the most I think the most intuitive generalization of the L2 norm, but they put an F down here, okay? And this is equal to equals 1 to n, j equals 1 to d. Okay, so I'm going to take all entries in the matrix, I square them, I sum them up, and I take the square root. Right? So if I took the matrix and I strung it out so it was an n times d dimensional vector, then this is the L2 norm. This is called the Frobenius norm. It says something kind of about this total size of the matrix. Okay? But there's a different notation for a matrix norm that has a 2 that's not this. This is called, I call this the spectral norm. Sometimes it's called the, it's an instance of an operator norm, which is a more general concept, which is pretty cool. I can rant about that sometime. Okay, but this is defined a little bit, and so in general, if I just write a matrix norm, it usually means the spectral norm, not the Frobenius norm. Okay. Okay, and this is equal to max of x in RD. Again, this was for A and n times d. So max of RD, where the norm of x is not equal to 0, of the norm of, okay. So this is, I look over all x, all possible d-dimensional vectors x, and I multiply x times a. I get a vector, so now this is a vector norm and the 2 norm, right, implicitly here, and then I divide through by the magnitude of x. So this is equivalent to max over x in RD, such that the norm of x is equal to 1. Okay, just a times x. Okay, so if I can multiply a by any vector, any unit vector, take out the scale of x, right? So I just care about the scale of a in some way. I can multiply by any vector. How big could that norm be? That's the spectral norm. this turns out it's also equal to the max of y in Rn. Let's say where y equals to 1. Can you see it down there? Let me just, which is y times by transpose, the normal by transpose A. Or is it, I guess, depends on whether it's a column or a row vector. Okay, it's equivalent. It gives you the same answer if I left multiply the matrix, or right multiply. It doesn't matter if I left or right multiply. But then I'm choosing them over n-dimensional vectors instead of d dimensions. It turns out it gives the same answer. We'll see why this is later on in the semester when we get into PCA and stuff, and eigenvalues and eigenvectors and how they relate to all this stuff. Okay, so this is the spectral norm. So these are the two important matrix norms here. Okay. All right, so there's much more about norms and distances and stuff in chapter 4. And the first part of it is talking about these LP norms. And then it gets into a whole bunch of other cool, more advanced. But if you want to know more, I personally think that's a great resource to look at. Okay.
So that's like a binary operator. You need like two, you need A and X. Is that correct? To get the norm, the spectral norm?
No, it only depends on A.
Where does X come from?
X, I'm maximizing over all choice of X. Let me write this up again larger here. Okay, so for A in R n n times d, the spectral norm is equal to the max over all x in Rd such that x equals to 1 of Ax. Okay, so one way of how to think about it is, and we'll see this a little bit later on in the semester, so you can think of, turns out you can think of, and we'll kind of see this later on, as a matrix A will correspond to something like an ellipse. Okay, so just pretend you understand this now. And I want to kind of give you intuition of what this x is corresponding to. And basically, when I look at the norm of Ax, that corresponds to, I pick, there's a unit vector, right? The ellipse doesn't necessarily intersect the unit vector. Okay, I pick, there's some circle, so I'm going to pick some x from here. This is all x such that the norm of x equals to 1, right? Is all the on here, right? And I want to pick the vector. And so if I pick this as x prime, then this length corresponds with the norm of Ax. This is effectively what's going to be happening. The length in this direction, x prime, right, is going to be the length of Ax prime on this ellipse. And so what the spectral norm refers to is the maximum over all of these. Okay, and so if I pick here, if I pick this as x star, where x star equals the arg max x such that x equals 1 of Ax, right? So the argument that maximizes this, then I'm going to get this length, and this length is larger than this one, right? So I can search over all possible directions, and I want to find the one that maximizes this quantity. And so I don't actually need this value x, or x star, which is the one that maximizes it. I just want to find the one that maximizes this length, and I want to return this length. This length gives me a quantity that measures essentially the maximum magnitude of A. Turns out X star will correspond with the first right singular vector of A, but we'll get to that later. Okay, so if you've seen that before, that corresponds to the same thing, but that and this turns out to be the first singular value is what this contains. Okay, we'll come back to that after fall break. Okay, it's a little bit tricky. The X doesn't actually appear anywhere. It's just I'm maximizing over the quantity. The operator norm, because X is the type of operator I can apply, and the norm is the maximum over all choices of operators from some family. Okay.
Is this something that you can do by hand, or do you just have to use numerical methods to find it?
You will use numerical methods, but those numerical methods are so good that you can kind of pretend that they're exact, basically. And we'll see how to compute them, one way how to compute them in class, and so forth. That's the power method, is what we use to compute this later in the semester. Turns out it's a very simple iterative algorithm, but it converges super, super fast. Okay, good. Let me start the next really important concept, and we'll probably finish this on Monday. Linear in the dependence. Okay. So let's say I've got k vectors x1, x2, up to xk, and these are all in Rd. And I've got k scalars, alpha 1, alpha 2, up to alpha k. These are all in R. Then I can create a new vector and this is also an Rd. So this is kind of, it turns out this is a really cool thing. It's kind of obvious from all the operations we've had before, but that I can take a bunch of d-dimensional vectors, k of them, multiply them by a scalar, and returns another d-dimensional vector. Okay. And So I want to say for such a set X, x1 up to xk, these are a subset of Rd. Then for any vector z also in Rd, such that there exists some alpha such that there exists some alpha scalars, some scalar values alpha, where z equals right. So if there exist these scalars, then we say that z is linearly dependent on x. Okay? So another thing, we're given the set x, we're given the vector z, we aren't given the alpha, we can choose any. If you can pick these alpha so that you can do this, you can recreate this vector z, then you say z is linearly dependent on the set x. And Otherwise, if this is not true, then you say Z is linearly independent of X. Okay, so let's start with a super simple geometric example. Maybe I'll do another kind of numerical example with actual small vectors in class on Monday. But let's say I've got a single vector x1. Okay, so this is just a single vector x1. Is Z linearly dependent or independent of x1? Independent. Yes, independent. The only linearly dependent points are those which lie on this line through the origin at x. Okay, I can scale x. If I want to make it, say this norm is 1, I make it norm of 2, I get a different point up here, 1/2 is down here, -1 is down here. I can get negative scaling as well. Gives me this whole line through here. But Z is independent. I cannot multiply this by a scalar. Okay, if I have a second point here, x2, then is Z linearly dependent or independent of x1, x2?
You still just have x1?
I have x1 and x2.
Now it's dependent.
Yeah, so it's dependent now, and it's because I can somehow add these two vectors together. Basically, what I can do is I can scale, say x1, maybe this is 2 times x1, and then I do something like minus 1.5 times x2, and that will give me the Z. Basically, if I have these two vectors which are not right on top of each other or negative of each other in the plane, then every other point in the plane, the two-dimensional space, is going to be linearly dependent on these vectors. I can always represent it, any Z, as some linear combination of these. Okay, I can always get to every point in the plane. Okay, and so so hopefully you've seen something like this before. In the plane, you can hopefully you can kind of see how you can do this by adding and scaling these together. But the nice thing about this is it generalizes to high dimensions in a nice way. In high dimensions, you're going to get this this subspace, a k-dimensional subspace or less. And we'll talk a little bit more about this. K-dimensional subspace that will include the origin, so it'll kind of slice through, say, 3-dimensional space. If I have a point that's off the board here, I cannot represent it by these two. So I have a 2-dimensional subspace of the board. If the vectors come off the board, then I'm kind of slicing through the origin through those two vectors. And every point Z on this 2-dimensional subspace I can represent, but not the stuff off of it. And so that's linear dependent and independence. I'll start from here on Monday, and we'll go through this a little bit more.